Which one? Oh, okay, this one. Let's try that. This is the one, right? Is this any better? I don't like see anything. I don't know. So I think I will switch back.
Because the background is white.
Yeah.
Maybe you can open the light.
I can try that. Is this visible for people? It did not help. I don't think it helps. So I would switch to the face camera. Yeah, I think this is fine. So, okay. So hi everyone. My name is Noman Bashir, and I am a postdoc working with Professor Prashant Shenoy. I completed my PhD at UMass as well with David Irwin last year. And since then, I have been working on topics related to sustainable computing and computing for sustainability. And that is going to be the topic of my lecture today. And ideally, I would like this lecture to be more like sort of discussion oriented rather than me just like talking about some of the things or delivering information. So if you have any question or sort of any comment, just feel free to let me know and we can like stop and like you can ask question at any point, basically. Okay, so we all know that the demand for computing has been growing exponentially over the last like decades or so, and it is going to accelerate even like further. So in this graph, I have time on x-axis and transistors per capita sold in a given year as a proxy for computing demand on y-axis. And then I have augmented like this graph with some of the key inventions that happened over the course of a year. So there are two things to notice here. First, that the key inventions during the earlier years of computing were far and few in between. Like it took like some really long time to make some major innovations. And second thing is that now the computing demand is increasing like exponentially, and it is like accelerating further and further. And in my opinion, there has been like a few key events that have shaped this future of computing. So one was the launch of public clouds such as AWS, GCP, and Azure. So this gave everyone an ability to run any application and just like rent things on demand, as opposed to like building their own data centers or servers whenever they like needed something. So on-premise data centers versus public clouds. So that was one of the big things in my mind. Second thing was the availability of personal smartphones. Like everyone now had a smartphone which had some capability to run applications as opposed to just making calls or like reading or sending texts. So these two things combined, I think, made a lot of like these applications that we see today like possible. And the third thing is kind of the rise of AI and the large language models that have like we have been saying. And I think as like these become more and more popular, like with chat gpt, you can I don't need to really talk about that, but um, the demand for computing is even growing further, and chat gpt along with like other large ai models are enabling a lot of like useful applications across like different domains of life. It's not just limited to computing itself. So there are work going on smart transportation, smart cities, precision agriculture, and basically whatever you can think, any aspect of life that you can think of, we can see computing playing a part in that uh, aspect of your life. So basically there is no end to this, and we are just like starting to deploy all of like these ai based or computing oriented tools to different uh, forms of life. And the nutshell from this slide is basically that the computing demand is just growing and it will accelerate even further. So what does this mean for, what are the implications of this increase in computing demand? So in my mind, I think there are two things. First one is like, let's just think of computing itself and not its applications in other domains. So in computing itself, when more and more people are using computing, you are increasing the energy demand of computing. So that is going up for sure. And computing enables like these different societal applications that we like use on daily basis. And some of those applications may be making things more efficient. So for example, there could be ride sharing apps that basically allow you to make use of like same car, like more people get to share that like car, and overall maybe the carbon footprint or the energy that goes into manufacturing a lot of cars, that is reduced. And similarly, I will give more examples later on, where you would see that the use of computing in other applications that we were doing like in a more sort of naive way is trying to reduce the energy demand of like those facets of life. There is a third angle to this, which is not often talked about, and that is, so when you have like some applications working, it motivates the need for or the desire for a lot more like applications or increased use. Chat gpt started working and a lot more people are using it. Now it is being used with the edge browser, so a lot more people will have access to it. So when, or even let's say like in some cases where people would have walked, they may take a uber now. Or so basically whenever you increase the efficiency of some process, the energy demand of doing that process reduces, but the overall usage of that application increases. This is called like G1s Paradox, and I will touch a little bit on that later. But the point here is, even though you are making individual applications such as like transportation, buildings, and whatnot, like all of them are becoming more and more energy efficient, but the overall energy demand of the society is growing. So then basically you have to kind of balance things out. So you have to not only look at where you are using, but so this is the second order effect of computing, and this is the third order effect, where you actually look at a holistic way from a perspective that, yeah, these things are making life easier and there are a lot of applications, but you also have to look at that within this earth, we can only emit so much carbon emissions in the world, or there is only a handful of capacity. Beyond that, if we go, that is going to like basically mean like the end of the world kind of thing. I don't want to be too dramatic, but like that is basically the point, that you don't just need to look at how computing is growing. It's a good thing. It has some positive, like not some, but a lot of positive things enabling societal applications. But then you also have to look at how it is impacting the overall thing and how like the demand increases as a result of it. Yeah, sure.
Oh, what a societal application giving humans more free time result in the person having free time? The notion of giving humans more free time is considered a negative.
So I don't think so. So the effect that I was mentioning here, it just focuses on the increased use as a result of efficiency and not how does that reduce time. But definitely that would be a factor, because if you can do for like travel within 4 hours instead of like, let's say, 3 days that you would normally take, now you have more time to like spend it, and you may end up consuming more energy. Yeah, that's maybe like some person have captured this factor as well, but to be honest, I don't know about that, but that's a good point. So but here I was just talking about, like, if you make an individual process more efficient, it necessarily does not reduce the usage of that.
Okay.
it
I see.
it increases the demand. Airplanes become safer, or like the uh, like air travel became very easy and not too much time consuming. A lot more people are using it nowadays. So that is kind of the thing where like which is mentioned, but like your point stands. Okay, the next question is that, okay, we have all this demand for computing, it's enabling applications. How is this demand being served? So there are different like scales at which we are serving the demand today. So it could be large scale, hyperscale, basically data centers, which have thousands of servers and data storage in them. For example, Google Dallas data center houses more than 100,000 servers, and it consumes 100 megawatts of power, which is enough to power like a small city. And these are probably outdated numbers, because I think there would be more data centers have like more data centers and bigger data centers have been built that may consume even more than that. And they are like huge facilities, 12 times roughly the size of a football field. And then apart from like these data centers, you may have like some smaller data centers that are located near the edge of like big cities to serve their demand. So they are called like edge data centers, you can call them. And they may have like hundreds of servers and be the size of a typical football field. And it may be like a few megawatt, like up to 5 megawatts or something. And then there are edge sites, which are basically the size of a room, and they have only a few kilowatts power consumption, and they may have a couple of dozen like servers. And at the end, like to the extreme end, you have like these mobile devices in your hand, like phones, and so they have like consume very like few watts of power and do all this like computation. And this is not necessarily a very strict or definition. Like anyone else may have like these different numbers about the sizes and how many servers they are and what is classified as an edge data center versus edge site, or what is truly edge. So these definitions are pretty much like fluid, but the overall message here is that the computing is being served in a wide range of manners, and it spans from your handheld devices today to like these big data centers. And today I will just talk about like these like big data centers and how their energy consumption looks like, and what we need to do to make these like computing through these data centers like more sustainable. So as I mentioned, we will talk about data centers. So what are the different attributes that contribute to data centers cost, energy, and carbon footprint? So these are kind of like the three things that we will mainly talk about. So in terms of cost, you have the cost of servers, you have the cost of building, like either you are renting or you are like you have built the building yourself. So there is capital investment, depends on the location. Servers are like they last every 3 to 5 years and they need to be replaced, not because they are not working, but because they have become sort of like more advanced or energy optimized servers have become available. And if you are paying a lot of cost to host those servers, you would rather host servers that take the same amount of space but do more computation with less energy or the same energy. So that is why they are replaced every 3 to 5 years, but actually they can easily last without like any big reliability problems. Like they can last for 10 years, but basically it's a lot more financial decision than a technological decision to replace servers every 3 to 5 years. And then if you look at the lifetime of a data center, like basically servers and buildings are not the things that cost the most. Energy consumption is like the major driving factor. In some cases, it's like I think 60-70% of your total cost, amortized cost over the lifetime is consumed is by consuming energy. So yeah, that is like one of the big factors. So and that energy is being spent on two things. One is actual computing, where you are running servers and doing some computation, and then the other one is basically cooling. So in cooling, because these servers are like massive sources of like they consume massive amount of energy. And if you know, like unless there are some mechanical parts, all of the energy that we consume is turned into heat. So if you, for example, have a very, very small LED and you put it in a box that does not allow like heat to escape, you would notice that the temperature of that box would rise like extremely fast and to very like high degrees. Because even with bulb or any societal process you can think of where you consume energy, it's always being released in terms of heat. So servers release massive amount of like heat because they don't have any moving part. All the energy is being converted to heat. And when you have this large density of servers packed into like a very small room, you need to cool them. And cooling costs a lot of like money, and there are different ways to cooling. And then the one thing that has received very less attention to this like date or like if you ignore last 2 to 3 years, carbon emissions from data centers or any societal application or infrastructure has received very less like attention. And the carbon emissions of a data center come from two things. One is the embodied carbon emission, which basically says that, okay, if I made or manufactured this server, there was some energy spent in manufacturing that server. And that energy presumably had released some carbon in generating that energy. And second, let's say when you dig the material or when you transport the material. So all of the things that went into manufacturing the server and bringing it into the data center, all of the emissions in that process are termed as embodied emission. And then there are operational emissions. Operational emissions are where you have this server and then you operate it, and how much emissions you are releasing. So of course, just like energy we like said, operational emissions are also from computing and cooling. So both of these things like contribute to the energy use. So we have these three things: cost, energy, and carbon. Okay, so now the question is like the title of this lecture, sustainable computing. What does that even mean? And how can we run these, like, how can we serve this computing demand that is increasing massively in a more sustainable manner? So sustainability can take a lot of different definitions. So an economist may say that a sustainability is that as long as you keep growing or like you have enough money. So some people may define it in terms of like having enough money to operate and whatnot. Other peoples may define it that if you have resources that you can always provide, it is a sustainability. For example, energy resources, if you have some, you can always provide those resources, that is sustainability. Then in our context, what we basically define sustainability is basically a goal to being sustainable is to operate as operate the infrastructure that you have in the least carbon intensive manner. And by that, what I mean is, when you use some infrastructure, you should try to emit as less carbon as part of that as possible. So that is the definition of sustainability that we will be using. So how can we do that? So as I said, embodied are carbon emissions from manufacturing, and operational are emissions from energy used for computing and cooling. So these are the things that we would like to reduce. How much carbon is emitted as a part of the manufacturing process, how much carbon you are emitting as a part of running your data center. So in this case, basically, as I said, we need to reduce those. So how do we do that? If you I have to compute the carbon footprint of any application, let's say I do a search, or if I run an inference request, serve an inference request, or run a training model, how do you even compute the carbon footprint? So carbon footprint is basically computed using this equation. So you have cycles per unit of work. So basically, this is the amount of CPU cycles or the computation that you do to perform a single unit of work, and you multiply it with how many total units of work you do. So if you multiply these two things, you would need to what you would get is how many total cycles of computing you are consuming. Then there are two other factors at the bottom. One is computing's energy efficiency. So computing's energy efficiency is basically how many cycles you can get out of your server per unit of energy consumed. So larger value is better. So if you have 100 cycles per unit of energy versus 10, of course 100 is better. And then there is energy's carbon efficiency, which basically tells that if I emit 1 gram of carbon dioxide, how much energy can I produce? So again, this value, the higher value, the better. So I have put some example numbers. For example, you have an inference request that takes 10 cycles per inference request. You have 100 inference requests, cancels out, it is 1,000. Then at the bottom, we have 5 cycles per kilowatt hour and 1 kilowatt hour per grams of carbon dioxide equivalent. So basically, under these settings, serving these 100 inference requests will emit 200 grams of carbon dioxide equivalent. So these are basically the goal of showing this equation was to show that when you have to determine carbon footprint of an application, what are the different factors that play a role. So I would like to take a step back before I talk about more of how to reduce carbon footprint. So actually, the question that I would like to answer here in this slide is, what has been the main driving factor so far in data centers? Now we want it to be carbon, right? But what has been the motivating factor so far in data center domains? There has been a lot of basically innovations there. So what drove that? So if you look at the cost of energy for a, let's say, typical data center, let's say you assume 100,000 servers, monthly cost of one server comes out to be around $50, and 100K server comes out to be $5 million. Then there is cost of cooling as well. So this value PUE, power usage effectiveness, it basically tells that how much additional power on top of your computing power you consume to cool those things. So a value of 2 means if you consume 100 units of energy to run servers, you consume another 100 to cool your data center. And it should be 1.1 PUE. So 1.1 would mean 10% extra. So that would be 5.5 million. Yeah. So basically it says that like cooling also like plays a factor, and in traditional data centers, like normally low scale data centers, this PUE value is 2. So basically amount that you spend on computing is same as on cooling. And there has been a lot of like efficiency gains, and the state of the art like Google and Facebook data centers, these like massive data centers, they have PUE value of around 1.1, which means you only spend around 10% more. So as the cloud, initially I said that public cloud platforms became available, there has been a shift from traditional or non-hyperscale clouds towards more hyperscale clouds. So these are the numbers which show that initially majority of the demand in 2015 or so was served by traditional data centers which had horrible PUE values. And then when these massive data centers became available through like these public cloud platforms, a lot of that workload shifted to these hyperscale data centers, and that shift continues to happen. So, and that has been driving. So what has been driving like this basically like transition is the cost of energy. So people wanted to use as less energy to run the same amount of compute as possible, because that meant like these big millions of dollars spent. So that like has been the case, and that has helped quite a lot. So there are like some predictions about how much energy consumption of the data centers have increased over the course of a year. So there are some estimates, because in 2005 and 2010, some people estimated that it will double every year. So they predicted it to be around like 550 or like 600 something billion kilowatt hour. And then there are some analyses that say, okay, it did not like actually increase that much, because all of these energy efficiency gains in data centers and low energy processors and less cost of cooling basically brought it down to this. But at the same time, some people say that this figure is not realistic, and actual value, actual energy consumption of the data centers is somewhere around like 900 billions of kilowatt hour. It doesn't matter which like basically number you believe here. There are two things to observe. First thing is that despite all of these like massive gains in energy efficiency that we have seen over the last few years, there was even the most optimistic estimates suggest that demand grew by some percent. And second thing is that if these estimates are not correct, it basically increased massively. And in future, these energy efficiency gains are not going to be there, because even if you drop your PUE to 1, you are not spending any energy on cooling. You are still spending energy on compute. So basically, as the demand grows into the future, you will be spending massive amount of energy on computing. So that is like sort of the key point. So demand is accelerating, but energy efficiency gains, we have exploited most of them so far. So to hit this point like really home, I would come back to this equation again and talk about what are the different sort of like fundamental laws that govern different components, and where are the opportunities for reducing the carbon footprint of computing. Maybe 1 minute. Okay, so cycles per unit. Cycles per unit is a bounded entity. If you want to do some computation, you can never do that computation with 0 cycles. You have to consume some cycle. Okay, and there has been a lot of like improvements in algorithmic efficiency to consume as less number of cycles as possible to perform like some work, to serve an inference request, to run an optimization model or whatever. So there has been a lot of work on that. Industry has very strong incentive to improve algorithmic like efficiency, and there has been a lot of like work on that. And even if you take these gains to like the extreme, you would still be consuming some amount of energy. So this is a bounded factor, and you can never like do anything about it. The second one is basically total units of work. This is unbounded thing. How much computing demands of applications is there? There is no end to it. People would build more applications, more and more people will start using it, and the demand will continue to grow. So data center capacity increased 6x from 2010 to 2018. And the crypto mining and ML demand, like it is outpacing Moore's law. So we are not able to fit the same number of transistor, like as many transistor as the demand is increasing. And industry has a very strong incentive to maintain and accelerate growth. They don't have any incentive to reduce demand, because more demand means more users, more money. And this is like how a typical like company which is investor owned, or like in a capitalistic economy, growth is basically it. So you have to maintain and accelerate growth, and that is the goal of companies, and they don't have any incentive to reduce that. So this will be unbounded factor. Then there is this like other computing's energy efficiency, which I said that it was how many cycles you can get per unit of energy spent. So there are different laws that go on that. So one is Launder's principle, which basically says that the theoretical limit of CMOS is going to be hit in 2050, or like theoretical limit, but in practically it will be hit much sooner. And then there is Comey's law, which says energy efficiency doubles every 1.5 to 2.6 years. But that has been mainly due to transition to cloud and dedicated hardware accelerators and whatnot. And like those gains are already reducing. And then there is G1s paradox that I mentioned, that historically gains in efficiency did not reduce demand. So basically this is computing's energy efficiency. To do some work of computing, you will have to spend some energy. So this is again bounded. Finally, this thing is energy's carbon efficiency, which is zero carbon energy, means basically efficiency can be infinite. So energy's carbon efficiency was how much energy you can produce per unit of carbon. So if carbon is zero, let's say, then basically you have that value as an infinite. So carbon footprint becomes zero. That can be infinite. And industry has been working on subsidizing like all these like green data centers and solar plants and whatnot. So there are a lot of like gains to be made by transitioning to low carbon energy and making sure your computing runs on low carbon energy. So this is also unbounded. So basically the point here is that that factor, total units of work, you cannot control. It is always going to increase. Cycle per unit work, computing's energy efficiency are bounded, and they will hit their limits very soon if they are not already hitting it. So basically, how can you reduce the carbon footprint then? Either by transitioning to low carbon energy, or if you have a not like zero carbon energy, if you have a carbon grid which has a variable carbon intensity over time, trying to exploit that. How can you exploit that? So basically, most of the work on sustainable computing itself is kind of in this domain nowadays. How do you exploit low carbon energy? Okay, so let's look at the grid's carbon intensity. What has the trends been over the year? So here you have like time on x-axis, intensity change in y-axis from 2001. So if you see and look at the world, overall, the carbon intensity of the grid, again, to define it, carbon intensity is basically how much carbon you emit per unit of energy. It is basically reciprocal of energy's carbon efficiency. So carbon intensity is 1 over carbon efficiency. So here you have like worldwide has remained kind of constant. Asia's overall energy carbon intensity has increased, and then Europe and North America has generally like decreased. And basically the point here is that carbon intensity has kind of remained same, and it has actually increased in parts of the world, but you cannot like ask people to not do that. For example, in countries in Asia like India, Pakistan, Bangladesh, like they are trying to grow now. Like they are trying to grow, so the carbon emissions factor is a very low priority on their agenda. Their first goal is to like serve their like fulfill the basic demands of their people, like food and homes and all of these things. Carbon emissions, so if they have to build a coal power plant to fulfill that, they will do that. And so basically you cannot really like control how the carbon intensity worldwide, like it may take a long time for it to go down. In Europe and North America, which have basically for years they have been emitting, and they have now started transitioning to low carbon sort of energy, they can afford like these kind of things. So I think like there is a kind of repatriation argument as well, that these big countries should subsidize the sustainability or green energy efforts in all of these other countries where they are just beginning to expand. So the point here was that grid carbon intensity has kind of remained constant, and you don't expect it to go down as much. So this problem of sustainability of computing is not going to solve itself on its own. We have to do something about it. So what can we do? So if we talk about, as I like mentioned a little bit earlier, that we need to use more clean energy and have like exploit all the variations in the grid. So let's like see how does that look. So if you look at this graph here, we have carbon intensity for a couple of regions for like I think 4 days. So if you see like Ontario has low carbon intensity overall, but it's variable. And then California has high carbon intensity, but its variations are much like more significant, and it follows kind of a periodic daily pattern. Maybe because it's like California has a lot more solar. So during the daytime, yeah, so this is kind of the daytime. So during day, you have basically a dip in carbon intensity because more and more solar is producing energy and serving the demand, and solar has like effectively zero operational carbon. So that is why it dips during the day. But in other cases, like you may have dip, like actually increase in Uruguay during the day, because over there, if there is not a lot of solar and people are using more and more energy during the day period, then you will have to run like these like big gas powered plants that emit more emission. So first thing is that like there are a lot of opportunities to, if you have to do some computation or train a model, should you do it here or here? So yeah, you should do it when the carbon intensity is low. I would go into this a little bit more, but let's take a look at this graph. So this basically also shows that which is mean carbon or average carbon intensity on x-axis and variations on y-axis. So basically, let's say pick Oregon or Delhi. So they have very high carbon intensity because they rely more on fossil fuels and coal, but their carbon intensity doesn't change as much because it's coal power plant, it's either running or not running. There is not a lot of variation. So there may not be a lot of like variations like that you can exploit. So if you are doing computing here, you may want to like shift your compute to a place like, I don't know what, like this is Iceland maybe. Okay, so Iceland has a very low carbon intensity, but it also does not have a lot of variation. A really good place to be maybe is Ontario. Ontario has low carbon intensity and a lot of variations. So it not only like moving from here to there gives you a lot of like carbon emission reductions, but also allows you to exploit these like temporal variabilities. So this is just to point out that a lot of regions in the world today are here, where you have some variations and carbon intensity is average carbon intensity is very high. And in future, at least I envision that a lot of regions from here would move from here to here, because as they integrate more and more solar, their energy carbon average carbon intensity would go down, but it would have a lot more variations. So it's a good news for sustainable computing that as more and more regions have low carbon intensity, but a lot more variations, you would be able to exploit that. So how do we exploit that? I think computing has very unique advantages that basically, in order to improve user experience and scale really well, computing has done quite a lot of things that are very beneficial when it comes to exploiting the variability of clean energy. So one thing, let's say a job arrives right now. You have so many options on how to execute that. You can run it immediately. You can move it to a greener place easily, like there is work on migration, like job migration. You can even do live migration of jobs, like job is running, something happens, machine goes down, and then you move it to another machine or another location. You can defer them. Let's say if a like ML training model, you can submit, like for example, here's a lot of people may be submitting jobs to Unity or any other cluster for that matter. You submit, and whenever the resources become available, it automatically runs. So basically over there, you are exploiting this ability to wait and then like run. You could run slower as well. Like if you have only one core available, you run on that. If you have more cores available, you can like basically parallelize and scale. And then you also have the option of running intermittently. Like there may be cases where you run and then checkpoint and like basically store all the states, and then maybe something else runs and you get to restore these things. So basically all of these capabilities of computing, even though they were driven by user experience, like they did not want end user to feel that the backend server of Google has failed and now you have to wait until they bring it back on. They had the ability to migrate stuff, start and stop stuff, run things faster, slower, and whatnot. So a lot of innovations that were motivated to hide all this complexity of computing and provide a simple abstraction layer are now very useful when you want to use the clean energy. And similarly, a lot of things were designed to scale well. People, or like all these big companies, wanted to scale to as many users as they could have, like especially in flash sort of crowd or situations where you will have a certain like surge of this request on Google or Twitter and Facebook, where you will have a lot more requests. So they wanted to have a capability to increase like massively. So that can also be useful, like the same techniques of parallelization and like scaling workloads that can be useful basically when, let's say, you have solar and suddenly solar energy becomes more available. You would want to run like faster at that time and then scale back down. So the point here is that computing is unlike many other loads that you see. I cannot basically, like if I need a light in this room, or if I need to basically toast my bread, I cannot delay it for like 4 days or like whatever, or even an hour or 5 minutes. Computing is very unique in a sense that it has a lot more flexibility. You cannot move your dishwasher load to a different location just because it has like low carbon energy there. So the unique advantages of computing and the tools that we have built over time make it a really good basically load for doing all of these arbitrage, carbon arbitrage in response to variability in carbon. Okay, so next, I will just take some water. If you have any questions, ask. Like I have been speaking nonstop. So the next thing is that, okay, we want to reduce carbon. Yeah, sure. In Iceland, they have a lot more hydro and nuclear power plants. So nuclear is assumed to be a zero carbon resource. So for that, like it has like very, very low. Yeah. Yes. So ideally, you would have very low carbon energy. That is like on average, if you are lower, that is the best thing, right? Like then you don't have to worry about when the carbon is high or low. You can just run there. But if you don't have that, if your average is high, you would want like these kind of variations, because then if you have some kind of flexibility in your workloads can be delayed by some point in time, they have some slack, they would be able to exploit that. So let's say I would prefer like maybe like even though like this is not a lot of like crossing here, but assume that there is a region in the world that is slightly lower than this. It still has average intensity is higher, but at some points its low points are basically lower than like this. So then rather than running here, if I am training a model, I would go to Ontario or that hypothetical region. I will wait and run when this intensity is actually lower. So if you have kind of flexibility in your workload, having variations is good because you can exploit that. But if you don't have flexibility, if you have web workload, web request coming in, then you basically like I don't think that then it matters a lot, because you have to serve them instantaneously, probably at the same location. So it depends on the workload that you have and what kind of flexibility that workload offers. So depending on that, yeah, yes. Yes, that's a, I mean, good question. And to be honest, I think so. There are two factors that play a role when people or the companies decide to be more green. One is the optics. How does a company is perceived as? So this is why you must have seen a lot of like recent talk about all this, like, okay, our shoes are designed like in a sustainable manner, or like all of this thing. Why is that? Because individuals have started caring about these things, and companies want to appear greener in their eyes. Okay. And even though like these big companies like computing, like Google, Facebook, they may not have like direct consumers that are forcing them, they still have like they want to appear green. That is one thing. And then there is also another thing. If you are a Google Cloud Platform or AWS you are running, you have a lot of like companies that are using your services. Let's say a clothing brand is using your computing services. Now, clothing brand makes a commitment that we will reduce our carbon emissions by 100% or 70%. They need to know how are your emissions going, like looking like, where they are emitting, and how to reduce them. So then they put a pressure kind of on these public clouds to show more information about their carbon emissions and offer them ways to reduce it. So basically, like this is one of the pressures that have been driving all of like this work so far, because currently there is no tax on carbon. So it doesn't matter. So there is just like cost of energy, and that does not include carbon cost. So it doesn't matter if you have used purely clean energy versus purely like brown energy, or which is highly pollutant. So there is no cost. But in future, there is an expectation that there will be a cost on carbon. So then people will be forced to take those things into account. But to be honest, in my opinion, currently it has been just like this realization that people care more about it and they want to appear sustainable. Okay, so I talked about accounting for and reducing carbon. So first, in order to reduce something, you need to be able to measure. You need to be able to tell how much energy or the carbon you are consuming. So these are, as I said, embodied and operational, and there is a lot of basically currently there is a lot of uh, disagreement over how one should look at these things, within the community, within people who work on sustainable computing and these companies. So someone says that embodied is more important because, let me give you two examples. One example is that if you look at your iPhone, if I look at the total life cycle of my iPhone, 80% of total carbon emissions are from embodied. Basically, it went into manufacturing and all of this. Actual energy usage of iPhone is very small. It maybe accounts for less than 20%. So here, in this case, definitely reducing embodied is important. But at the same, for a server, that split may be opposite. You may have 30% or 20% going into embodied and the rest is sort of operational. So it's just a matter of what you are looking at and how you are looking at. So one view is that, which I share, and this is my personal opinion, that if I am talking about embodied and as a data center, my embodied emissions are basically someone else's operational. So they should be if everyone reduces their operational emissions, embodied will automatically go down. But they are good to have, basically putting pressures on manufacturers to be green and things like that. But I don't in my mind, operational should be prioritized because this is something that is directly under your control. And this is not a solved problem. You can do a lot more in this domain without going into these supply chain issues. And these are the kind of things that I don't understand. I'm not an economic expert or supply chain issues. I don't get those things. But as a systems person, what is under my control is this operational. How do I operate my workload and reduce the carbon emission? So this is my opinion, but I think there are a lot of other people who take a different approach. They say that we should weigh them basically equally, and they even add them, which I don't understand because that may lead to double counting. I am counting embodied emission for myself as well as the people who supplied servers to me. They are also counting. So I don't know which way is exactly the right uh, way, but I think the nutshell, both should be emphasized, but it may depend on context. Okay, so one other thing is, so what does all of this mean for sustainable computing? So first thing that we need to do is this prerequisite, basically some of the things that we need to do. If you just go and search sustainable computing, you will find a plethora of different terms and jargons that you won't understand, and everyone would think they mean the same thing. Carbon free, carbon neutral, zero carbon, 100% renewable, net zero, all of these things mean different things. And they can be confusing for people. If someone says that we are net zero, it doesn't mean that they are not using any sort of brown energy or any coal, fossil fuel powered energy. What does carbon free even mean? So there are a lot of terms that need to be clarified, and I'm not going to do that here, but this is something that I think we have, our lab has a paper on this. So if you are interested, you should go and take a look at it. Then once we have sort of a common consensus on terminology and what each thing means, then what we need to do is that we need to enable visibility into carbon. So there are companies like Wartime and Electricity Map. They have developed their APIs. So if you are building some application, you could easily integrate their APIs into your applications, or you can play with that. I think Adam even built a like simple toy, like a example that where he like used their APIs to compute carbon emissions. So basically you can do that easily. So now there are tools available that tell you how much energy, how much carbon you are emitting when you are consuming energy in some place. Then there is this whole discussion about average versus marginal, that is like a separate thing. I won't go into it. But then basically the high level point is visibility. You should be able to know how much energy you are consuming and how much carbon that energy consumption is emitting. Then basically we should be shifting focus from energy to carbon, because it doesn't matter in some sense how much energy you consume. It matters how much carbon does that emit. I can afford to be a little less energy efficient if I am running off solar. But if I am running off fossil fuel or coal powered plant, I would want to be highly energy efficient. So basically the focus should be in some, with some sort of qualifications, it should be on carbon and not energy. And then finally, this is something that I have discussed like quite in detail, that we should leverage the computing flexibility and unique advantages that it offers, and not only reduce the carbon footprint of computing, but also help grid in like offering some services that, like, I think if you are interested, you can find that. And ultimately, we would like to go towards a carbon-free grid where everything is basically renewable or like very, very low carbon. So now the other aspect, like so far we have discussed computing and how can we make computing itself sustainable. So now I will give a very brief overview of how computing is making other societal applications more sustainable. So, okay, so these are just like two use cases. First one at the top is improving building and transportation like sectors. So they like think of these applications in sort of like three steps: sense, analyze, control. So for example, in buildings, you will have sensors enabled by computing that basically monitor energy consumption, monitor what the temperature of the home is, how much like what is the occupancy, if there is anyone in the room or not. And then basically you use computational tools to analyze the data that is generated from these sensors. And once you have analyzed it, you do some action, you control, like if there is no one in this room, turn off the lights. If there is no one in the room, turn off the AC. If you know, if you have learned a pattern that someone is going to come at 8 a.m., rather than turning on the AC at full speed at that time, you may start like cooling the room a little bit earlier to either reduce energy consumption or provide them more thermal comfort and whatnot. And so all of like this loops in the building are enabled by computing in one way or another, and they allow you to operate buildings much more efficiently. So similar case can be made about transportation. I don't think like we have time to like, I would have liked to ask people and provide the information, but like they like basically the cars can sense with EVs and all these like autonomous vehicles, you can sense like which other cars are there, where the congestion is, and you can avoid congestion, increase your fuel efficiency, or simply like all of like these things you can do. And similarly in agriculture, there is a lot of like focus on precision agriculture, where rather than just like you pushing or spraying like whole pesticides on a lot of like the whole field, you may have computer vision enabled cameras that are taking pictures and detecting pests and or early signs of basically disease, and then you do targeted spraying and of pesticides and removal of weeds and whatnot. So all of these things, agriculture is another field where it can be easily computing can help increase the efficiency of your crops. So I will go a little bit deep into the building monitoring thing. So there are different options available for power monitoring at home. There are outlet level power monitoring. For example, like you could plug a meter here and you can monitor how much your laptop is consuming when it is charging, or how much your, I don't know, uh, iron is consuming. So that could be like one of the things. And then there could be meters that sit outside your home and do the total energy monitoring, and there could be like smart meters. So metering, monitoring itself is enabled in various ways at various levels through computing. Then basically you analyze the data. So you can use statistical machine learning and modeling to gain deep insights. When are people inside home, when they are not, which homes have inefficient furnaces, heaters, or dryers. You can compare data across multiple homes to see that, okay, this home is consuming abnormally high energy when the washer is on. What is going on? And are you wasting energy or in your home? Is your AC schedule aligned with occupancy pattern, and how does that impact the overall grid? So basically, by analyzing the data using the meters that I mentioned in the previous slide, you can do a lot more analytics enabled by simple statistical techniques or machine learning to optimize your resources. So an example could be that, like, basically you have this occupancy sensor at the right, and then you have like some kind of maybe like a smart microcontroller or something. It senses that data, and that occupancy sensor is also feeding this to a Nest or smart thermostat control. So here you can basically, based on this, you can say that like this is a away period. So in that, on that basis, you may have like different sort of analysis of when the people are away depending on the day of the week. And basically you will create a chart or schedule that this Nest control basically employs to reduce energy consumption in your home. So this is another example of computing used to make things more and more sustainable. Then basically, if you think of computing in other domains, there are two angles to it. Either you reduce the energy consumption of applications, or you help them use low carbon energy more efficient. So one thing is that there has been a lot of like significant growth in renewable energy production. There has been these even smaller rooftop wind turbines, solar PV, solar thermal for water heating. But the problem with them is they are highly intermittent. Like their output can change very quickly because they are impacted by environmental variables such as clouds, temperature, and maybe dust and things like that. So how can you enable like household appliances or anything else for that matter to make a better use of these renewable energy resources? So there is a lot of work on forecasting solar energy. You can use your past data to build models on top of it, use weather forecast data from like National Weather Service and whatnot, and use machine learning to train your model that predict like solar output, which is like a big domain in itself now. It is kind of saturated, but still there is a lot of like value to providing accurate solar power forecast or demand forecast. And then another use case could be EV charging. So let's say you have solar panels and then you are forecasting their power using computational resources. And you know, like later in the day, the solar power energy is going to be high. And if your cars are parked inside your parking for the whole day, you may want to delay their charging till the point when solar is really high. So this is where, again, you are using computational resources to make another application, which is transportation, more sustainable and less carbon intensive. And to summarize, there are two aspects: sustainable computing and computing for sustainability. In sustainable computing, one thing is that demand for computing is growing, and we need to serve that demand in a sustainable manner. Previous things that have worked for in computing, which were mainly energy efficiency gains, they are becoming more and more limited. But computing has given us like quite a lot of unique advantages that allow us to exploit clean energy. And we should focus on optimizing carbon efficiency, which is basically how much carbon you emit when you do a 1 unit of work, and also focus on reducing the operational emissions as well as embodied emissions. And in terms of computing for sustainability, we can leverage computing to reduce energy consumption, or also allow basically different sectors to use low carbon energy or zero carbon energy like solar in a much better way. Yeah. So any questions? It's fine, like you relax, you can go. Yeah. So generally, I think they are pretty accurate. PUE values are pretty accurate because like I think there are regulations around those monitoring and reporting of how much you are spending on cooling and all of those things. So I think those values are pretty accurate. So that I think is definitely believable. As far as like being net zero while you are, let's say, working, like you have a data center in Delhi, let's say, which has like quite high carbon intensity. So how are you even net zero there? So there are a lot of like financial or accounting magic that these companies do. To some extent, this is a controversial take, but basically there are like they would buy like green energy somewhere else. So there are things called carbon offsets where you incentivize or buy these carbon credits somewhere else, and you get to claim that you are net zero. But Google is trying to go towards 24/7 matching, which is basically at every hour of the day you produce the same amount of energy in the same grid. So that is much stricter form of carbon offset, which is better. But still, that is not the end, and there are different problems with that as well. But I think till this point, there is a lot of like financial magic going on. But at the same time, like it should be acknowledged that these big companies at this point don't have any real incentive to do these things, but they are choosing to do it. So, and they are leading the way as well. So I think, yeah, it's kind of like both. You have to appreciate them, but at the same time, know that what they are doing may not be the best. Like it should not stop other people from making an effort towards sustainable computing. The problem with their message is when they claim to be, because we submit papers to these conferences, and some of the reviewers like said to us in a paper that your approach of trying to optimize for carbon is not needed because Google says that they are going to be net zero or something like that, carbon free. So if their message basically misleads people, then it is wrong. Otherwise, whatever they are doing, that is definitely like helpful. Yeah.
Just wondering.
I have worked on quite, I think, like all of the angles that I discussed here. Initially, during my PhD and even before that, I worked on more of a computing for sustainability. Even though the carbon was not goal there at that time, it was more of energy, trying to develop better forecasting and how to integrate solar into the grid. So it was more of leveraging computing and the lessons like tools that there are available to make energy or grid more sustainable or more efficient or reliable, whatever. And then recently, like last 2 3 years, it has been more of sustainable computing itself, where we have looked at how to basically make use of these like low carbon energy, like better use of these low carbon energy resources, and how can we build systems that allow like application developers or users to exploit this like variations in carbon and things like that. So it has been kind of like this I think represent like around 60 to 70% of the threads that I work on. Like I did not talk about specific techniques that we build because it was supposed to be high level. And if you want to know more, just go to Prashant's website, and there is like a lot of like I think information about how uh, like like the relevant topics or the people who worked on it or the papers that there are. Because I think in addition to like just academics working on it, if you are going to go tomorrow and be a developer or somewhere or software architect or something, you need to know about these things. Because like one other uh, criticism that we face in research is that when you are like people said to one of our papers that when you are trying to do all of these things, provide information about carbon and change things, it increases the complexity for application developers and software architects, and they would not want to do that. So basically then we had to say that like today they may not be incentivized to do that because their company is not incentivizing them to do that. Like if the company has some carbon cost or some, like then the application developers and software architect would need to account for that as well. Currently it's just about using less resources, as much less resources as possible. So the point is that even though like this research may be very specific down the line, like if you look at individual papers, but as far as a higher level goal for computer scientists to be to develop systems and applications that are more carbon aware, I think that is something that applies to everyone, because there is a lot of like discussion on how ML carbon footprint is like becoming massive and massive, and with these large models it would even increase. So how do you tackle that? As like basically nowadays it's the focus is on, if you are 89% accurate, the focus is basically on being 90% accurate. But how much does that result in, like how much additional energy you need to gain that 1% of accuracy improvement? So things like that need to be put into perspective. And yeah, so at some point you like, for some applications where you don't even care about the accuracy that much, it doesn't matter if for a toy application something is able to put my face right on top of like I don't know some cartoon or whatnot. It doesn't matter the accuracy, but do you really need to use that accurate model there? It is just a toy application or something. So these things are important for everyone to consider, I think. Yeah, so the class is done. If you want to leave, you can.